record. Okay. Hello again. So this week we have covered the rotations and the rotation groups. And so as a result, I'm going to summarize some of the things in here. The reason why we are giving special attention to this is that because in most of the physical examples of group applications of group theory, the symmetric groups will be the rotation groups. So I don't know, we will have like a molecule with a triangular shape, for example. And in that case, the corresponding symmetric group will be the symmetric group of the triangle, but that would be a rotation group, right? And so as a result, I mean, we have to see some certain properties of these groups, perhaps, and I don't know, some certain relationships, actually. For example, we would like to describe the conjugacy relationship and things like that. But in any case, so as a result, I mean, we have to actually say something about these groups and finite subgroups of such rotation groups. Okay. So I'm going to start describing this rotation group, rotations in general, and then I'll talk about the rotation group. So first of all, a rotation is actually a transformation of a vector. Right? So you can actually think of it like that. Rotations, basically transformations of vectors. It's not just an arbitrary transformation. Of course, it's a rotational transformation. But so I'm going to specify this a little bit more in here. So I'm going to think about this n dimensions. I can write down a vector in the n-dimensional space in terms of the components like that, and then there are these unit vectors, let's say E1, E2, and En, let's say. So in general, sorry, En. Okay. So in general, a vector is going to be described by this kind of a unit vector notation in n dimensions. So applications will be like either two-dimensional or three-dimensional, but let's just do this discussion for general n-dimensional rotation. So to make this notation better, from here we would like to pass to the column vector notation. So instead of using this kind of a notation, I'm going to describe a vector as a column vector, a column matrix. It's an n by 1 matrix. So I usually call them as column vectors, but probably an alternative name is a column matrix. It's basically an n by 1 matrix. Right? Okay. A rotation is therefore a transformation of this vector to another vector. A rotation is like that. So therefore, sorry about that. So a rotation basically maps a vector to another vector, and we basically express this relationship by some kind of a functional relationship. So this is essentially a linear transformation in here, and I would like to express this as a matrix transformation. So essentially, this is going to be an n by n matrix in here. Okay. Meaning that I would express the components of this rotated matrix. So let's write it down like that, the n prime, as some kind of a square matrix in here, multiplied with v2 vn, the components of the original vector. So we have like some components in here, some matrix elements in here, and so R21, R22, and so on. Right? In any case, I mean, let's not just go carry. Let's not be carried away, but I mean, this actually has to be a square matrix in here, whatever it is. I can also write it in component form in here. So essentially, this is the matrix R that we are going to talk about, and a rotation can actually be expressed as a square matrix like that. Okay. So this is a transformation that actually fixes the origin, right? So you can actually think of this as a transformation that keeps the origin the same. So that means that a vector with a zero vector is going to be converted into a zero vector. So that's one of the essential things. There won't be any translation or anything like that where zero is converted to a non-zero vector. So therefore, we can write down the relationship like that. Okay. And a rotation has this important property that it basically preserves length. We say that R is length preserving or norm preserving. Length preserving. All right. I mean, the proper term that mathematicians use is actually norm preserving. Norm is the same thing as the length. If the idea is that the length of this vector is the same as the length of the rotated vector is the same as the original vector. Right? This is for all V, for all vectors V. Right? So that's, I'm going to take this as the definition, right? So, basically, these kind of transformations is actually met a lot. So it not only contains the rotations that we think of, but it also contains the reflection transformations and things like that. So in general, I'm going to call all of them as rotations, right? So in any case, but first I would like to express this mathematical relationship of what does that mean in terms of that matrix, right? So first, let's just remember this. The length of a vector is basically the sum of the square root of the sum of the squares of the components. Okay. I can actually describe this length as in terms of the matrix product. So it's the transpose of the this column matrix. So transpose is going to give us the row matrix. So the product of this with the column matrix is actually going to give me a 1-by-1 matrix. But this 1-by-1 matrix, I'm going to usually treat this as a number and not as a formal matrix, right? I mean, in reality, in applications, usually this is a load. It appears that it's a load. So a 1-by-1 matrix can always be treated as the number that it contains, right? So I can treat them as a number. So therefore, this product in here, that row vector with this column vector, actually contains this. If you remember the matrix product, you just need to take the product of the corresponding elements in here and then sum them up. So here, this is going to give me the sum of the squares of the components. Okay? So that's the length. So let's just remember this. So this VT is the transpose of the matrix V. Basically, you have to convert every row, every column into a row, and vice versa, right? You can actually think of it like that. In any case, so by using that transformation, I can basically express the length preserving property like that. So that's length preserving property, but instead I use it for the square. So that means like V prime transpose V prime in terms of the matrices can be expressed like that. But V prime is essentially R applied on V, right? But in here, the transpose of the product of two matrices is equal to the product of the transposes, but in the opposite order. So as a result, on the right-hand side, I have like product of these four matrices in here. Here we have the product of two matrices. I can think of the right-hand side as like there's an identity matrix in here, whatever. So I can basically transform that equation into this equation. We have a square matrix in here, which is obtained by R transpose R minus identity. It is multiplied with V transpose, which is the row vector in here, and V from right, and the result is 0 for all V. Okay. You can show that, but I don't want to show it actually. This basically implies that R transpose R minus identity is equal to 0. So this implies that the R transpose R is equal to identity. Okay. So we just called a matrix that have this property as an orthogonal matrix, right? A square matrix, sorry, a real, all right, let's just, sorry about this. A square matrix, right, with a square matrix R with real entries, right? Entries should be real numbers, so that's one requirement. It has to be a square matrix, it's n by n, for example, is called an orthogonal matrix. If basically the inverse of the matrix is equal to its transpose. Okay, it's basically that relationship in here. So the product of two matrices being identities is basically the same thing as saying that these matrices are like they are inverses of each other. Okay, so that's our definition of an orthogonal matrix. And so here basically I'm going to associate a rotation as an operation an orthogonal matrix. Okay, so that's the idea in here. So in here, basically, we are going to take the definition of a rotation as an orthogonal matrix. So as a result, I can think of the rotation transformations as the this set of, well, I'm going to think of a rotation group as a matrix group, basically. Where the, yeah, whatever. But before going to the group, let's just express on this. So R is orthogonal, is equivalent to the statement that R transpose R is equal to identity. That's the same thing as saying that R transpose is equal to identity. And that's the same thing as saying that the inverse of R is equal to the transpose. So it is easier to take the inverses of such matrices. Okay? I'm going to write down a few important properties for these. But let's just give one more definition in here. So R is orthogonal is equivalent to the statement that the R inverse is also orthogonal. Why? Because, well, I mean, think of it like that. R inverse is equal to the transpose. So as a result, this matrix satisfies that property. The product of the transpose of that matrix with that. Since the transpose of the transpose is the same thing as the matrix, that's going to give us the identity. So therefore, the inverse also has to be also an orthogonal. Okay, so identity is also orthogonal. An identity matrix. So as a result, the orthogonal matrices actually form a group. So this is actually called O2, sorry, ON. Okay. So that's basically the set of n by n orthogonal matrices. Okay. The set of n by n orthogonal matrices. So ON is a group. Right? So that's what's important for us is this. So the product of two orthogonal matrices is also orthogonal. So sorry about for not adding this, but that's basically, I mean, I need to check all the group properties basically, right? It's an associative product and whatever. Okay, so there's another thing in here. It's about the determinant. So if R is orthogonal, right? R is orthogonal. Implies that R transpose R is equal to identity. Now, if you just take the determinant of that equation, determinant of identity is equal to 1. So we have this. So the left-hand side can be written as this. So product of determinant of the product of matrices is equal to the product of the determinants. And the determinant of the transpose is the same thing as the original matrix, right? So this then tells you that the determinant of an orthogonal matrix has a square which is equal to 1, which implies that the determinant is either +1 or -1, all right? So as a result, we classify, therefore, the orthogonal matrices into two kinds, right? If R is orthogonal, then we say, so in that case, we say R is a proper orthogonal matrix if the determinant of R is equal to +1. And we say that R is an improper orthogonal matrix if the, whatever, I mean, there's then in here, the determinant is equal to -1. Okay. So as a result, we basically classify the orthogonal matrices into these two kinds. Basically, proper means, improper means, basically there are some reflections in it. And then proper means just the proper rotations. Let's say ordinary rotations. When you think about the rotation, basically, these are the ones that would be actually, that we call as the proper ones, right? So as a result, we have like these two special kinds of rotations. So it appears that, I mean, the determinant is actually, so let's just say it like this. Determinant is from O2 to the numbers +1 and -1. I can think of this thing as basically cyclic group, right? And since the determinant of the product of two matrices satisfy that property, right? Determinant of S, right? So as a result, this is actually a homomorphism, right? Determinant is a homomorphism. I mean, it's a group homomorphism. So in general, if you have a matrix group, then the determinant of that matrix is actually a homomorphism to some kind of a subset of real numbers or complex numbers or whatever, in general like that. So the kernel of that homomorphism is basically is what we call as SO2, SON. Right, so basically, the set of proper orthogonal matrices of size n by n. Okay. SON is this. So in any case, I can actually think of it like this. So this is a subgroup, right? SON is a subgroup of ON. So ON is called the orthogonal group. Orthogonal group of dimension n, actually. SON is called the special orthogonal group. Okay. Now, the idea in here is something like this. So you can actually think of it like this. So O2 can actually be divided from the middle into two parts, actually. One part is, sorry, it's not O2, ON in general. I mean, since today I talked about O2 a lot, I can actually, I have this confusion. Okay, so the orthogonal group can actually be divided equally into these two parts. One is just the proper rotations, and the other one is basically the rest. Right? This is ON minus SON in terms of the group set notation. So this other part contains improper rotations, right? So these are proper rotations and improper rotations. Their sizes are actually the same. Unfortunately, we cannot count the size because all of these groups are infinite, except when n equals 1, but n equals 1 is just an irrelevant situation. So n equals 2, starting with the 2 dimensions, all of these groups are infinite in size, so they are actually continuous groups. But at least the size of this special orthogonal group is just the same as the size of this one. Right? You can make actually a one-to-one correspondence between these two parts. And so basically the determinant actually takes +1 value on this half and takes -1 value on the other half. So this is a subgroup of OM, and that's the coset of that subgroup. Okay, so because of that, I can actually form this quotient group relationship. So that's actually one of the homomorphism theorems. So this is actually the kernel of the determinant. So that's basically isomorphic to C2 in general. Okay. In any case, all right. So the next thing that I do is this. Right? Basically, R is orthogonal. If you remember, we just defined this as the length preserving. Okay. But now I'm going to show that this is actually a more general statement. It's actually a dot product preserving. So the idea is this. So suppose that I have a vector V in here and another vector W. Okay. And then I rotate them by some rotation. And I obtain a vector V prime, which has the same length as V and W prime in here. All right. So in any case, so V is mapped into V prime, which is R times V. W is mapped into W prime, which is R times W. So in that case, okay, so the idea in here is this. The dot product preserving means that the dot product of these two vectors after rotation is the same thing as their dot product before the rotation. Okay, and the reason is this. Basically, this dot product is equal to V1 times W1 plus V2 times W2 plus Vn times Wn. So the dot product can be expressed as the sum of the products of the corresponding components. Okay, but I can express this as V transpose W in terms of the matrix product, and similarly, this dot product can be expressed in the same way. So there's also a corresponding term here. So the idea in here is this. I mean, it's basically the same calculation. So this is V prime transpose. So that's R times V prime transpose. And that's R times W prime. Sorry. There's no prime in here. This is R times W. But this can be expressed as R transpose R. I mean, this product. But since this is equal to identity, because that's an orthogonal transformation, I get this, right? And the right-hand side is basically that. So the length preserving property is essentially equivalent to the dot product preserving property. Okay. Now the idea in here is this. I mean, let me just write this thing down in here. So if that angle is theta and that angle is theta prime, right? If you remember, we can also express the dot product in terms of the lengths of the vectors and the angle between them, like that. Cosine of the angle between them. And so V prime dot W prime is equal to V prime W prime cosine theta prime. In any case, so since the rotations are both length preserving and dot product preserving, it also implies that it's also angle preserving. So the angle between two vectors do not change under these kind of orthogonal transformations. Okay. So that's the next property. Second property is this. Well, that was the second property. Third property is that if I have two vectors which are perpendicular to each other, or unit vectors and then perpendicular, let's say, I don't know, let's call this like n, and let's call this like m. The angle between them is 90 degrees. After a rotation, they are going to be transformed into, again, unit vectors and perpendicular vectors, right? So the vectors that they are going to be transformed will be still unit vectors and perpendicular. I mean, it's just a special application of the above properties. What we have is something called the orthonormal basis. In general, we use these kind of things a lot in, I don't know, in some certain places. Orthonormal. Yeah, let me write this. Right, a set of vectors. I don't know. Let's say A1, AN is called an orthonormal basis. Basically, orthonormal means orthogonal and normalized. In usual or ordinary geometry, we actually, instead of normal, we just call them as unit vectors, and instead of orthogonal, we call them as perpendicular vectors, right? But that's the term that people usually use, so therefore that's what I'm going to use, right? If each of these vectors is a unit vector, right? So that's the normalization condition, basically. And, well, basically, the dot product of any two of them is equal to 0 if when the vectors are different from each other. And there are these two conditions in here. Okay, but I mean, because of I mean, this is expressed in terms of length, and this is expressed in terms of the dot product. Sorry about that. I need to say one more thing. Sorry. We usually express this as the AI dot AJ is equal to delta IJ in terms of the Kronecker delta. So basically, the dot product of a vector with itself is equal to two different vectors, their dot product is equal to 0. So that actually summarizes like that. In any case, since these rotations preserve the dot product, because of that, we just express it like this. So under a rotation, each of these vectors are going to be transformed into, yeah, let me call this like AI prime, let's say, it's rotation, after a rotation by r, let's say. In that case, so A1 dot 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 AN is an orthonormal basis, implies that the rotated vectors are also is an orthonormal basis. Okay, this tells you that a rotation essentially converts an orthonormal basis to another orthonormal basis, or something like that. I mean, the best example is the Cartesian directions, basically x, y, z. Okay, after a rotation, these are going to be transformed into some other direction. So x prime will be like that. So that's x prime, y prime, and z prime. What we are saying is that after this rotation, so these are also, mutually orthogonal set of unit vectors, basically, right? That's what we are saying. Okay. All right. There's this next property in here. Well, there's something called the standard basis, first of all. Standard basis, sorry, of n by 1 column vectors. Standard basis is basically the basis where, formed from the vectors where one of the entries is equal to 1 and all the rest is equal to 0. Okay. So there are actually n vectors in here. So they actually correspond to the coordinate unit vectors usually. We actually think of them like that, right? So this is an E1, E2, and En is an orthonormal basis. Okay. So that's the first thing, right? The second thing is that if I have a square matrix R, right, it's an n by n matrix. Okay. So there are some entries in here, right? Yeah, whatever, and let's just show it like that. What happens is that this first column in here, so that's the first column. This is really equal to R applied on the first standard basis vector. So you can actually check this by yourself. Convince yourself that this is really the case. Otherwise, I cannot explain it in here. So by using your, I don't know how you do your matrix product. If you do this matrix product, you will just notice that, yeah, the first column gives you RE1. And similarly, the second column is actually RE2. So that's the second column. It's equal to RE2. Okay. So as a result, I can think, I have a nice interpretation of the columns of a matrix like that, right? This is kind of useful for if R is an orthogonal transformation, because then I can interpret this RE1, RE2, whatever these columns as basically the transformations of the orthogonal, this orthonormal, the standard basis, right? So therefore, let's say it like this: columns of an orthogonal matrix of an orthogonal matrix is an orthonormal basis. Okay. Now, because of the fact that since if R is orthogonal, R transpose is also orthogonal too. So therefore, I can basically do the same statement for the rows of an orthogonal matrix, right? So as a result, I can perhaps take the orthogonality of a given square matrix, for example, by just looking this property or the next property. And so as a result, it's kind of easier to check the orthogonality by using these kind of properties. Instead of doing a full matrix product, you can just check this, because sometimes it's easier to see these than to write down a matrix product. Okay. So mathematically, there's actually some kind of we can express it in a nice statement like that, right? Let's say it like this: if R is an n by n square matrix with real entries, then the following are equivalent. So the mathematicians usually use these kind of statements actually. They just write down a list of statements. Any one of them is actually an alternative definition of the concept of the matrix being an orthogonal. So R is orthogonal. That's the same thing as R is length preserving. Okay. Sorry, Yeah, R is orthogonal means that its inverse is equal to the transpose, right? So that's how we define it formally. But we have obtained this from this length preserving property. So orthogonal and length preserving basically is synonymous. So if a matrix is orthogonal, it's automatically length preserving. Or if it's length preserving, then we can easily say that it's orthogonal. Number three, R is dot product preserving. Number four, R maps n orthonormal bases to n orthonormal bases. Okay. Number four, but it's expressed in a slightly different way. Instead of mapping a single, it maps all orthonormal bases to orthonormal bases, right? So it maps every orthonormal. So it's enough that R maps a single orthonormal basis to another orthonormal basis. This then implies that it actually maps all orthonormal bases to all the other one. So columns of R is an orthonormal basis. I mean, above, I have just shown that this is equivalent to number 4 in here. So the same thing is for the rows. Okay. So that means, like, I mean, I can take any of these as a definition of the orthogonality, orthogonal matrix. Okay. So as a result, it's kind of useful from different points of view. Okay. So in any case, I'm just going to use this fact, for example, to discuss the group in O2, right? So let's say that R is an element of O2. So therefore, this is a 2 by 2 matrix, okay? So it has like these entries, but I can use these, use that fact to actually guess what kind of entries these are. So I know that, for example, rotation in 2 dimensions is basically a transformation of this XY plane, right? So for example, this x-axis is transformed into some other vector actually. So let's just call this like R times X. Okay. So obviously, the first column in here, right? This is basically the components of the X prime. Okay. And I can use these kind of arguments and things like that to say something about this matrix in here. So as a result, what I'm going to do is this. So I'm just going to suppose that, well, this is the XY plane. So I'm going to assume that this X prime in here has an angle theta, measured from the x-axis, obviously. So theta can be between 0 and 2 pi. All right. So I'm just going to take this as the positive value. In that case, R can be, the first column of R is cosine theta and sine theta. Okay. So it is normalized, right? It is a unit vector, obviously, and theta is some kind of an arbitrary parameter in here. In any case, so since the y-axis is perpendicular to the x-axis, y prime should also be perpendicular to it. So as a result, there are 2 possibilities for y prime. Sorry about that. So it is either that, where that angle is theta, or it's just the opposite of that. So if I use this direction, so I don't know, this is also a possibility for y prime, where the angle is theta. So as a result, I'm going to write down the components of either that vector or that vector as the second column in here. But I have 2 options in here, 2 possibilities, right? 2 options. And I just have a different name for that. So one of them is R theta. So that's cosine theta, sine theta is the first column, obviously. So it is this choice in here. So therefore, this is minus sine theta and cosine theta. Okay. And the second option is, well, it's just the negative of this second column, right? So the first column is the same. In this case, I just multiply the second column with -1. Okay, you can easily check that. The first one is a proper rotation, a proper orthogonal matrix because its determinant is +1. And the second one is, well, it's improper because its determinant is equal to -1. Okay, so that's the first thing. Okay. So the proper ones, well, inverses. So, I mean, since each of these, the inverse of each of these matrices is equal, well, since these are orthogonal, the inverse can be expressed as the transpose of these matrices. In the transpose, the diagonal entries remain the same, but the off-diagonal entries are exchanged. So therefore, for R theta, we have this. Okay. Basically, this is just like basically changing the parameter theta to -theta. Okay. For J theta, you can see that the inverse is itself. So that's J theta transpose. Whatever, I mean, that's cosine theta, that's sine theta, sine theta. So off-diagonal entries are already equal to each other. So therefore, it's J theta. So that means like J theta is a transformation whose square is equal to identity. So this is actually a very strong indication that J theta is a reflection. But I don't want to go into the detailing here. I'm just going to express it like that. Okay? But for R theta is like that. This basically is a transform, it's actually a rotation by theta. So this is the x-axis, this is the y-axis. So in that case, the x prime is this axis and y prime is that axis. And so it is quite easy to see in here that this is rotated by theta and that's rotated by theta. Okay, so that means for any kind of a vector in here, whatever that vector is, I don't know how to draw this. So let's just call the vector v in here like that. Yeah, I'm just going to draw it in a second picture. Sorry about that. So if I have any vector in here, just convince yourself that this r times r theta applied on v is actually a vector where the vector is rotated by theta. Okay. So in any case, so therefore r theta is actually a proper rotation by angle theta. Okay. So because of that, it satisfies these properties like r theta followed by r5, for example, is a rotation by theta plus phi. And so therefore, this is the same thing as rotation by first by theta and then by phi. Okay. So a proper, I mean, you can also check this algebraically as well. No problem with this. But logically, it basically corresponds to the fact that in a two-dimensional rotation, a rotation followed by the other one is actually a one single pure rotation by an angle theta plus phi. Okay, so this implies that SO2, which is essentially the set of these proper rotations, where theta is between 0 and 2 pi, is an abelian group. Okay. So that's the first thing. This is abelian. It just depends on, I mean, all the rotations in here depend on just an angle parameter. Let's see. If I take r theta in here and then take the nth power, in that case, I get r n theta. And it's just the inverse is just a special case of that. So that's r minus theta. Okay. All right, that's it. So for J theta, actually, I'm not going to show in here because I don't have much time. But we can actually think of it like that. So that's the x-axis, that's the y-axis. So we just think about some kind of a the line in here, where the angle in here is equal to theta over 2. Right? This pink line in here, this is actually what we call as a mirror axis. Mirror plane. Since this is like a line, I can actually call this as a line. In 3 dimensions, every mirror has a mirror plane. Right? This is actually a direction. Sorry about that. I mean, if there is a vector in that direction, so let's call this like this. M is a vector in mirror plane. This implies that J theta applied on M is M. Okay, so this is the plane, this is the set of vectors which are left invariant by this transformation. Okay, so in a mirror, for example, in a mirroring transformation, a reflection, the mirror plane is left invariant. Okay. On the other hand, there's actually a perpendicular direction in here. Sorry, let's just show it like that. Okay, in that case, that angle is theta over 2. Sorry, that's theta over 2. So that's, I'm going to call this as the mirror axis. Okay. If I call this unit vector along that direction, so on the mirror axis, basically J theta applied on a vector in here is going to change its direction. Okay, so we just take the mirroring along the axis basically, which means I'm going to do it in here in the last minutes perhaps. So this is the mirror, and this is the mirror axis, right? These are perpendicular to each other. They are perpendicular. So if I have a vector in here, vector V, that makes an angle of, I don't know, alpha to that with the mirror in the reflection. So J theta applied on V is basically a vector like that, where that angle is alpha. Okay. So the idea in here is this. So I'm going to use a very thin color line in here. I can express this vector as a vector which is parallel to the mirror plane plus a vector which is perpendicular to the mirror plane, right? After a transformation, the parallel component remains the same, but the perpendicular component changes sign. So therefore, the vector is transformed into this plus that. So therefore, it's transformed into the other thing in here. Okay. So just think of it like that. And so as a result, this kind of makes sense actually, right? Okay, so I'm going to leave that in here. But yeah, let me just make a note in here. So like, I would like to say something about finite subgroups. These are also in the notes. Finite subgroup of O2 actually. I'm kind of interested in this because if I have a shape or a molecule and whatever, symmetric group is a rotational group. Usually the symmetric group will be actually a finite subgroup of the rotation group O2. Okay. So as a result, I need to have a way of actually counting all possible finite subgroups. Let me quickly say this. In this case, if G is a finite subgroup of O2, let's say it like this. G is a finite subgroup. Finite means there are actually a finite number of elements. In that case, there are actually 2 possibilities. One of them is that the G can actually be a rotation group containing only pure rotations, in which case it's essentially a cyclic group, or it's the symmetric group of a regular angon, and in which case it's called the dihedral group. So that's the dihedral group. That's the cyclic group. Okay, so there are some explanations in the notes as a result. I don't have to explain how we actually reached that result or the details. I mean, you may want to read this part in here. So there's actually a corresponding theorem for the three-dimensional rotational groups as well.